In this video, we're computing the geometric area bounded between two functions that intersect. And what I mean by geometric area is that we need the area contributions to all count as positive. So our example is to compute the geometric area bounded by f of x, which is 3 minus x squared. That's the upside down parabola in the picture. And then g of x, which is 2x. That's the line in the picture. And we're trying to get the area bounded on the x interval -1 to 2. So to start setting up the area here, we look at a thin rectangular slice of the region on the left. Now because f of x is above g of x in this region, a positive height for this rectangle will be obtained if we take f of x minus g of x. And the width of this thin rectangle, that's an increment of x, an infinitesimal increment of x that we'll call dx. So we can say that for the left region, our area contribution dA is equal to f of x minus g of x dx. Now to the right of the intersection of these two curves, the line ends up above the parabola. And that means to express a positive height so that we get positive area, my height has to be called g of x minus f of x. Again, the width of that little area increment is called dx, and we can write down the infinitesimal area contribution for a rectangular slice right of the intersection. And that's going to be g of x minus f of x dx. Now there's one more complication to deal with before we start setting up integrals. We have to actually figure out what the intersection point is. And I'm just going to call that x. Now to find the x value of the intersection, we use the fact that when two curves cross over each other, they have the same x coordinate and the same y coordinate. So if we use the fact that f of x is equal to g of x, in other words, the y coordinates are the same, when I choose this value of x, all I have to do is plug in the formula for f of x, that's 3 minus x squared, and the formula for g of x, and I end up with a condition on the intersection, 3 minus x squared is equal to 2x. Now, oftentimes when you're looking for an intersection of two curves, particularly if you involved transcendental functions, there may not be any analytical solution to this, and you'll have to use technology to approximate the intersection. But for this introductory problem, I made it so this results in a factorable quadratic. So what I'm going to do is move all the terms to the right-hand side. That gives me a 0 on the left-hand side and a positive x squared plus 2x and then minus 3. So all we have to do is guess the factors of this. And if it factors into two binomials, they must each start with an x, so I get an x squared. The constants give me a 3, so I know they have to be a 3 times 1. And I want a positive cross term of 2x, so I'm going to make the larger one positive, so plus 3, the smaller number negative, and then I just double check. I get x squared plus 3x minus x, that gives me a 2x, and then minus 3, so it's good. So we get solutions to this equation if either factor is equal to 0. If x minus 1 is equal to 0, we have a solution, and that would mean x is equal to 1. We get another solution if x plus 3 is equal to 0, which would mean x is equal to -3. So -3 is entirely outside the region of interest here. This does mean that these curves intersect twice, and one of those is off to the left at x equals -3. But the one we're interested in is x equals 1. That's the intersection that's in the region of interest. So for the height of our rectangle, we're going to use f of x minus g of x all the way from the left end of our interval, which was -1, to the point x equals 1. So our left formula will be used on -1, 1, where f of x is always above g of x. Our right formula is going to be used on 1 to 2. And now we're ready to set up our integrals. So to write down the total area, I use an integral to sum up all these infinitesimal contributions, these dA's. And we'll start with the integral on the left. That's an f of x minus g of x, which is going to be 3 minus x squared minus 2x dx. The limits of integration are from -1 to 1. Then we write down the area for the right side. That happens as x goes from 1 to 2. And the area contribution there is g of x minus f of x. So that's a 2x minus f of x, which is a 3 minus x squared. I may as well distribute the -1 while I'm at it. And I get a -3 plus x squared dx. Now all we have to do is guess antiderivatives and evaluate across the endpoints. The antiderivative of 3 is 3x, x squared. That gives me a 1/3 x cubed using the power rule. -2x, that gives me an x squared, so minus x squared. That's evaluated from -1 to 1. Then we have an x squared minus 3x plus 1/3 x cubed, evaluated from 1 to 2. So we sub in the upper limits and lower limits. Remember, you subtract what you get when you sub in the lower limit. And I notice a slight shortcut here. In this quadratic term, x squared, if I sub in 1, I get 1. If I sub in -1, I get 1. So when I subtract the upper limit from the lower limit, the contribution of that term with the even power isn't going to matter. So we'll sub in the upper limit here in the first expression, and 3 times 1 is 3, so I have a 3. Minus 1/3, because 1 cubed is just 1. Subtract what you get in the lower limit, which is going to give me a 3 times -1, or -3. And then -1 cubed is -1, so I have a plus 1/3. In the second expression, I sub in the upper limit, and I end up with a 4 minus 6 plus 1/3 times 2 cubed, in other words, 8/3. And then for my lower limit, I plug in 1, and I end up with 1 minus 3 plus a third. Now for my first two terms, I see that I have a 3 minus -3, in other words, 6, and a -1/3 minus another 1/3, which gives me a -2/3. In my second two terms, something really nice happens. 4 minus 6 is -2, but 1 minus 3 is also -2. So I end up with a -2 minus -2, in other words, -2 plus 2, which is 0. So all that's gone. Then I end up with an 8/3 minus 1/3, which is 7/3. This gives me 6 plus 5/3. Writing 6 with a denominator of 3, that's 18/3, plus 5/3, and I arrive at my answer for the area, 23/3, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.